it all up. Is it not working at all?
He knows who he is. He knows he's now on my list.
Nolan. Oh.
You're next on the acorn list. Ask him a little bit about the acorn. Alrighty, everybody. So, workshop. We have Dr. Jason Furtado here. He's going to talk a lot more about the weather challenge. If you haven't heard of it yet, it's a really great thing, and I will give it over to Dr. Furtado.
Okay, thanks for letting me get a chance to speak with you guys for a few minutes. So like Sean said, I'm here to talk about Weather Challenge. So Weather Challenge is a national forecasting contest, actually developed and started here at OU. The forecast contest, though, there was an old version that was run by Penn State for many, many years, and then in 2005-06, it's transitioned over, and now OU runs it. So actually, the national manager is right here in this building, Dr. Jeff Rosara. Actually, my coming office next to me. So, like I said, it's a national forecasting contest. So what do? You're competing against students, all levels, sophomore, senior, graduate students, faculty, staff, competing against everyone across the U.S. and even some schools in Canada. And you're competing basically for bragging rights to be the best forecaster in the country, on the continent, if you will. And so the contest runs, starts actually next week, so I'm doing signups now. And it runs actually, we have a fall semester, fall, spring, so we rotate sites every 2 weeks. Next week will be actually QS Florida, S4. And we'll be forecasting that at the end of January. We start with Seattle, which is where the AMS contester. Only Seattle is chosen. The rest are going to be called range forecast, and usually weather happens in the next forecast site. So you never really know. You get to the spring, some speed across the country. So it's nice. When I started undergraduate, I did the old contest, and I was a freshman, and I jumped right in. And it was a great learning experience. And that's how you learn forecasting. That's sort of my model. It's sort of like anything else. If you want to be a great baseball player, if you want to play the piano well, you got to practice, and do it. And the only way to be a good forecaster is to practice, folks. So I think this offers a great opportunity to practice forecasting, and it's fun. So you can compete against, like I said, you're competing against other schools. You're also competing individually, and you're competing as a team. OU has a team, so we forecast. We compete as a team, and we compete individually for the prizes. So again, the way the contest works is things are actually broken down. And so there's actually 4 categories. So as you're forecasting for as a team, you're also forecasting within each category. So for example, if you're a freshman, sophomore, you're competing in the freshman, sophomore category. If you're a junior, senior, there's a junior, senior category, grad students, and then faculty and staff have their own category as well. So although you compete against everyone, you also have prizes within your own category. So you don't have to feel like, well, a sophomore or whatever. By the way, that does happen. Just because people have been forecasting for many, many juniors and seniors. So like I said, OU has a goal of, as a team. The second goal is we'd like to beat Penn State. So Dr. Rosara's class for his thing about beating Penn State. So that's our goal. So we have 2 runs. So you get to forecast for different cities, compete against people, you get trophies. So trophies and plaques for the first and second. Like OU, we have a special scholarship. The best undergraduate forecaster at the end of the year gets $500. So there's also a little money incentive here if you're part of the OU team. I think that's basically the contest. So again, you run every 2 weeks. So we start next week and we run every 2 weeks for different cities. We forecast 4 days a week, Monday through Thursday, and you're forecasting for the next day. So the things we forecast for, we forecast four different things. We forecast, so there's the categories that I mentioned. But we forecast for 4 things. Maximum temperature, max temp in Fahrenheit, minimum wind speed in knots and the maximum total accumulated liquid precipitation that falls. And these are all within a 24-hour period. So the temperature and the precip are all between 6 Zulu and 6 Zulu. The wind speed's a little different. It goes by the climate report, which is good. But again, you're forecasting, so those are the 4 things. So every day you're making a forecast. So starting Monday, team members will all be making a forecast for Key West. The maximum temperature, the minimum temperature, the highest wind speed that will be recorded in 24 hours, and then the total amount of precipitation, so in hundreds of it. And you'll do that for each city. So those are the 4 big criteria. As a team, we've kind of pulled some resources together. There's some people that started a Facebook group last year and share some information. People do some biases online to share that with people. So again, there's a team atmosphere, but there's also your own individual competition. So, almost done. Are there any questions about the contest? So again, we're looking to get, yeah.
Are you guaranteed to do all those cities, or do you get knocked out?
No, you do not get knocked out. That's
So
a
you
good
can
question.
still just do
You
it?
do, yeah, you go on city by city. So, like, and I've had it happen, there's a city that I'm terrible, there's a terrible at, I don't know, Key West, maybe I'll just be terrible at, but it doesn't knock me out. I keep going city by city. And some people are like to be terrible on the first city, or at one city, and are great at the other. It could be an advantage, for example, if some of you are from Pennsylvania, maybe you know something about Harrisburg, Pennsylvania, or Key West. People have been working in Key West for a while, so maybe they know some good. The other thing too is when we rank your scores, so your scores are done by the normalized score, and for each semester you drop your worst city. So the worst city doesn't count towards you. So you can do really bad in one city and it won't count towards your final score. It gets dropped. So it's really the average of your 4 best cities in that semester that goes for the semester. And then at the end of the year, it's the best 8 cities, or best 4 from the first 4. So you can do really poorly once. Yeah.
Is it like a daily commitment?
Monday through Thursday. Yeah, Monday through Thursday. So when you enter your forecast, which will be right on this site. So again, it runs 4 days a week, Monday through Thursday. So you submit your forecast. So for example, if you were forecasting for tomorrow, you would insert all of these values in here. And then you do have the option. So let's say you're going away, or you've got something going on the next day. You're not able to forecast. You can actually enter up to 3 forecasts ahead of time. And I always suggest people who do this contest to always at least, so there's the option of manually putting in a forecast, or you can choose the guidance forecast, so it takes whatever the GFS loss output is, and that'll be a forecast. There's a persistence forecast, but no member of the OU team will ever put that one, ever. And so you have the option. So for example, I always click guidance for all 3 days because sometimes things happen. The next day something happens. It's 6:45 and it's like, oh crap, I didn't do a forecast. At least there's something in there. By the way, if you miss a forecast, the forecast that gets entered for you is climatology for that day, which is pretty terrible most of the time. And you get a 10-point Yeah, so the deadline, actually, I need your entry form by Friday. Because the contest starts on Monday, I have to enter everything by Sunday. So I need your form by Friday. The contest is, it's $5 for the full year. And if you want to be eligible for the scholarship, to compete for that, you have to sign up for the full year. Also, in the spring, after the 10 cities, we have a tournament. Okay, NCAA's tournament of forecasters, the top 64 forecasters go against each other head to head. If you want to qualify for that tournament, you also have to sign up to be the full year. So if you decide, I'm going to try for the fall, and then you do awesome in the fall, and you want to sign up for the spring, and you do awesome in the spring, you're not eligible for the tournament because you didn't sign up for the full year.
Also, what's the daily deadline for submitting?
So the daily deadline is 0 Zulu time to enter forecasts. So for example, Monday, everyone who's participating has to enter their forecast by 0 Zulu, which is 7 p.m. Central Daylight Time. And the forecast period starts at 6 Zulu Tuesday to 6 Zulu Wednesday. And that's how it runs. When daylight saving time ends, then it goes to 6 o'clock. So you have to enter your forecast by 6 and go off the daylight saving. So by 7 until November, and then 6 is the deadline. So you can enter at any time. So you don't have to enter at 5:55, like I said. If 12 o'clock you have a free few minutes to enter your forecast, you can enter the night before, you can do it. Want to enter 2 days before, you can do it. So it's really any other questions? Okay. So, I don't know the best way to do this, but I can leave the forms on the side.
Yeah.
So my office is 5240. So it's right by Dr. Sarah's office on the north side of the building. So go all the way to basically on the direct other side of this room, all the way on the other side. So if you're interested, and I really encourage you, again, if you want to do forecasting, you want to learn stuff, this is a great way to do it. Sign the form, bring me $5, and bring it to my office by Friday.
When you enter the forecast, it should be for the whole week? Or
Nope,
for the
just that day. You're entering a forecast for every day.
So
So, like-
Sunday I entered for.
Monday, or you can start on Monday.
Okay.
Yeah, so Monday, runs Monday, Tuesday, Wednesday, Thursday, Monday forecast, 4 days. Just 4 days a week, Monday through Thursday. So when you enter a forecast on Monday, it's for Tuesday, 6 to Wednesday, 6. And then you enter forecast on Tuesday, it's for Wednesday, 6 to Thursday, 6. Yeah, and you only enter it Monday through Thursday. So no Friday, no Saturday, no Sunday. Any other questions?
Well, thank you very much. Okay, so now we have PhD student Addison Alford and the very fine Dr. Kevin Clay. Further comments? You ready to go?
Almost. Do it. Move it over.
Set up all the, we've got the live stream.
Make it a little bit easier, right? Yeah.
Very exciting. This is one of the
Is your video
first times
good,
we've
Ben?
been doing this for our workshop, so you guys can actually show this to all your friends who didn't make it, or if they're interested in radar or anything like that, if you just want to sort of share the stuff you're doing here. We'll have the video recording of this presentation up on YouTube, so you can check that out. Really great stuff that we're doing here. And thanks to Ben Holcomb right over here for setting all that up for us. All right, so all systems go? Awesome.
Good? Okay. Thanks, everyone, for having me. I do apologize in advance. I came down with a cold yesterday, so I sound a little nasally at the moment. But today, I am going to be presenting radar. With great transmit power comes great responsibility. And yeah, radar joke there. So many thanks to multiple people for helping put this presentation together, whether they knew they did or not, including Dr. Clazel and my advisor, Dr. Mike Bickerstaff, here in the building. So first and foremost, radar history. A lot of you guys here are freshmen, sophomores. Raise your hand if you're a freshman. Yes, Andrew, you're a freshman. Yeah, Ben too. Yeah, sophomores? Oh, wow. Y'all need to get your class more involved. But yeah, freshmen, whether you know it or not, radar was actually developed in World War II because Hitler is bad. So radar was originally developed for military purposes, but when they were working with radar, they realized they could see weather targets. And to the military, that wasn't a very good thing because you wanted to track missiles and airplanes instead of weather targets. But meteorologists took that and developed the 1957 and 1974 weather surveillance radars that did not have a Doppler velocity capability. So in 1988, the WSR-88Ds were put into the Weather Service, and that is what we all see today. And you can see here a guy hanging off the side of a WSR-88D as he works on the radome. But the D stands for Doppler, and that means there's the capability to detect motion toward or away from the radar. And I emphasize toward or away only, and we'll talk later about why that's important. A little more radar history, and if anyone, I know one person at least, has seen this slide before. If any of you were in my class last year, you saw this slide about mobile Doppler radars. These came into being in the 1990s, 2000s. We have quite a few here, but no, we do not have the dowels here. Freshmen, this is your first lesson. The dowels do not exist here. They were actually built here. But Doppler on wheels is actually the name of Dr. Josh Werman's radars. Dowels does not refer to every mobile radar. So here in the School of Meteorology specifically, we have the smart radars here. And then at the Advanced Radar Research Center across the street, we have Raxpol and PX1000. There are others. So we don't have the dowels here. If anyone ever tells you, oh, look at the dowels in the vehicle bay. No, they're not the dowels. Okay. And yes, that's my first rant for the night. But OU doesn't necessarily just have mobile radars. The dowels aren't just at CSWR in Colorado. There are other radars around the country, the Texas Tech KA bands. Florida State has a C-band mobile radar, but I do believe it is out of commission at the moment. And the University of Alabama X-band Doppler radar. So multiple ones of these are dual polometric radars, and I'll talk about dual pol here in just a little bit. So how does a radar work? Radar stands for radio detection and ranging. And the easiest way to discuss exactly what that means and how radar works is radar sends out a pulse of electromagnetic radiation. It bounces off of hailstones, raindrops, whatever, in the middle of a thunderstorm. And then part of that energy comes directly back to the radar receiver. And then the nice picture that the TV meteorologist or you're looking at in radar scope is put up on your display, and then you can see it. But that's not it. That's not the only thing. We don't send just one pulse and then that's it. We send multiple pulses. Why do we do that? Does anyone know? Multiple pulses. Is one measurement a good idea? If we take just one single measurement of any variable in the atmosphere, is that a good idea? No. Why?
You want to get one snapshot in time.
Yep, that. But if I were taking temperature measurement and I were looking over, say, 10 minutes or so, but I wanted to represent that 10 minutes with one number, what would I do? Take an average, right? So radar sends multiple pulses as it along one radial, in one direction. Before it continues turning, it's sending anywhere from 16 to 256 pulses along one radial to get an average measurement of not only the power that's returned to the radar so that you can see things like reflectivity, but you can also get a better idea of your Doppler velocity, or how you would think of like a bat sending out sound waves via sonar and listening for that. So you take multiple pulses to try to come up with the best measurement of both your reflectivity and your Doppler velocity. Now, does a radar just see Does it have a pencil beam when it sends out a pulse of radiation? Is it a pencil beam? Raise your hand if you think it is. Good. No one did. So obviously you can see the diagram here. So as the radar sends out a pulse, that pulse actually widens with distance as you continue out into the atmosphere. And each one of these little bends here are the individual bends that you see if you're looking at a radar display. And that bend length is a function of how long you actually transmit your pulse. So that determines the radial resolution of your radar. So you can see the equation, simple equation down here, length of the pulse equals transmit times the speed of light. And then as that pulse goes out, again, like I said earlier, it scatters off some target way out in the distance, and then only a small fraction of that power actually comes back. Does anyone know how small that fraction is? You should know. Not you. Well, you should. You were in my class. You should know. You work for ARC.
It's really small. I don't remember the exact number. But yeah.
Any guesses? 1/100th? Good guess. So 10 to the 2. Other guesses? Try 10 to the 10. Yeah. That's the amount of power that's actually coming back to the radar. 10 to the 7 was getting close. But 10 to the 10 less amount of power than what is transmitted is coming back to the radar. So the receiver for a weather radar has to be incredibly sensitive to actually be able to hear, quote unquote, that pulse coming back. And here's the equation that solves everything. Freshmen, it's okay. You will survive, okay? This will actually seem very easy by the time you finish your degree. So the power return to the radar is a function of all these random variables that I'm not going to talk about, except for this one right here, Z sub h. Does anyone know what Z sub h is? Come on, people that took my class. Kelton. Radar reflectivity factor, yes. Thank you. So that is not the radar reflectivity factor that you're used to seeing, though. This radar reflectivity factor is the summation of all of the droplet diameters raised to the 6th power in a radar volume. How many raindrops might that be in a thunderstorm in a radar volume? Say a radar volume the size of a football field. How many scatters would that be? I don't even know the number. I'm just wondering if y'all are going to say anything. It's a lot, okay? So this number right here can range from 0, 1, to millions and millions, okay? It can range, it can vary greatly. So to put it in perspective for us as humans, we put it on a log scale and multiply it by 10. So that's the number that I was just showing you. That's the summation. And then this Z sub h, and you'll notice capital H versus little h, that is the number that's output on the display that you might read on RadarScope. So in, say, just for example, 1 cubic meter volume, you have 5 drops. And all of those drops have a diameter of 5 millimeters. Your reflectivity factor would be about 49 dBz. You would see on, say, a weather service display, you'd see something like yellow or orange, something like that. But it depends on your scale. And just here's another example of what you might see with radar reflectivity factor. This is from the Moore, Oklahoma tornado in 2013. And this is taken from the TDWR just before the tornado touched down. Touchdown at 1947 UTC, so this is about a minute before. You can see the hook echo here. Pretty much everyone here should know what a hook echo is. I think you've all seen it before. And then you have a lot of precipitation, heavy precipitation in the forward flank of the supercell. You're getting up, I don't have a scale on here, but I can tell you that's about 60 to 65 dBz or so. And then way out in the forward flank, here in these whites and greens, you see radar reflectivity returns of about 20 or 25 dBz. So everyone generally should know how to read that, I hope. If you are unfamiliar with radar scope and you want to get it on your Mac, for example, and this also applies to the iPhone app, you can pull in radar reflectivity using this little drop-down box here at the top. I've just taken a screenshot. This was taken last Friday when I was actually making part of this presentation. And then you can choose from all these different options here. Radar reflectivity, base reflectivity. This is super resolution reflectivity. So what's actually happening is there's no way to get this super resolution. The radars didn't just magically change overnight and they're now super resolution. Okay? What's actually happening is you're oversampling in your azimuth. A WSR88D, does anyone know what the beam width of a WSR88D is in degrees? What is the azimuthal resolution of a WSR88D? It's about 1, if I remember correctly. Yeah, 1 degree. But the super resolution is actually them oversampling every half degree. Yeah. So the radar beam width does not change. But where they're actually plotting their data does change. And they plot it every half degree. And this is only if you use the, I believe, Weather Decision Technologies display. They actually go and resample that data and then actually output the data at the super resolution. And I think the Weather Service now in AWIPS, that also is possible. One other thing that I want to draw your attention to here before I leave reflectivity, and yeah, you can see where I've got my OU and then home plotted here. You can actually put locations for yourself in radar scope. But the other thing I want to point out is you probably need to leave it in expert mode, and this projector isn't in focus very well. But there's a little expert mode option somewhere in here. And the reason I say leave radar scope in expert mode is because I say so. And I'll tell you why in just a little bit. But I just want you to kind of remember this picture, okay? But as far as radar reflectivity goes, it's a pretty easy field to understand. It's based on the power that comes back. It tells us how heavy the precipitation is. But are there problems with reflectivity? What are some of the potential problems? What do you think these targets are in the circle? Is it rain? Birds, bats? Here's some suggestions. What else? What else could it be? Bugs. Wind farm? Any other suggestions? What? Yep. Fires. Yeah. So this is actually anomalous propagation, and it's hitting ground targets of probably trees, buildings, power lines, all sorts of different things. And that happens when the radar beam undergoes what's called super refraction. Okay, so standard refraction of a radar beam, the radar beam does not just go out straight, it actually bends down slightly in the atmosphere. But when you get a really strong inversion, and when might that happen? When might you get a strong inversion? Sorry?
In the morning.
Oh, in the morning, yes. In the morning. When else? Evening. Frontal passage, yes. You see it actually quite a lot with frontal passages as the front gets nearer and nearer the radar. So as that front passes, all these targets suddenly show up behind the front. And that's because the inversion is so strong that it's actually bending the radar beam down, and that is actually returning power to the radar. You can actually see ground targets based on that. So if you see these kinds of targets where you see this nice supercell, we all kind of know what a supercell looks like. You might even see some multi-cell convection here. That looks meteorological to us. But look at the texture of these. The gradient and reflectivity around these maxima, it's really, really sharp. Okay. The texture, as my advisor likes to call it, is very dense. And so that might be an indication of ground targets or anomalous propagation. So going back to that picture earlier of the Moore, Oklahoma supercell where I showed you heavy precipitation, you've got reflectivity upwards of 60 dBz. how many of you would agree with me that when I say 60 dBz, there's hail there? Raise your hand if you'd agree. No one? Really? Okay, we've got one. That's like, I don't know. Well, I've heard a lot of people say that before, so I know there are some people in this room that would agree with that. So, if that statement were ever said to me, I would say very bad things to that person. Things that I'm definitely not going to say, especially when I'm being live streamed all across the country. Not going to say that. But to help me express my rage at people that do say that, I brought in Gordon Ramsay. Gordon Ramsay is very expressive. If you've ever watched the show Hell's Kitchen or Kitchen Nightmares, I'm a big fan of Gordon Ramsay. And this GIF definitely says everything that I would ever say to someone that says, radar reflectivity, 60 dBz, there's hail. Why would I be mad? Why would I be mad, guys?
That could just simply just be really heavy rain.
It could just be simply heavy rain. How might I find out? Seniors, juniors, you know. Dual polarization, yes. Thank you, Kelton. Dual polarization. You've talked about power return, just simple power return. Now it's your responsibility to understand dual polarization observations, such as differential reflectivity, correlation coefficient, differential phase, and specific differential phase. All of these variables together, and if you use them correctly, you can truly understand what the radar is telling you and what it's not telling you. And I really want to emphasize what it's not telling you. So they can tell you different things about the hydrometer shape, hydrometer concentration, and the type or lack thereof, because we don't just see hydrometers on radar returns. So what is dual polarized weather radar? So a conventional weather radar, or Doppler radar, as the WSR-88Ds were originally built, sent out one pulse in the horizontal. You get back reflectivity, Doppler velocity, and spectrum width, which I'm not going to cover spectrum width in this talk. But with dual pole radar, you send out a beam in the horizontal and in the vertical. So you have two independent measurements of whatever is out in the sky, and you get signal back in both the horizontal and the vertical. So if I take the ratio of the power that is returned, or the reflectivities, both from the horizontal and the vertical, I might see what's called ZDR, or differential reflectivity, where ZDR that has a value of greater than 0, that means there's more power being returned in the horizontal than there is in the vertical. So that might mean something like an oblate raindrop. Are raindrops shaped like teardrops, guys? I hope everyone says no. I really hope so. And if they do, Dr. Clazel himself will charge you $1. And he'll take, you take cash check? All? Okay. So it might be a raindrop, or it might be an insect. What are insects shaped like generally? Are they longer in the horizontal or in the vertical? Horizontal, yeah. So they might send back more power in the horizontal, okay? Or you get a ZDR near 0. That indicates that the power in both channels is approximately the same. So that might be a spherical hailstone. Hailstones aren't necessarily spherical, but in radar they generally show up as spherical. And graupel. Anyone know what graupel is? Yeah.
Graupel isn't hail, it isn't sleet. It's like water that's frozen.
Yeah. So it's being rimed. Okay. So there's supercooled liquid water in the upper portion of thunderstorms, and as that hits something, it instantly freezes. That forms graupel. Okay. So graupel can be spherical, or you can have conical graupel, and actually have a ZDR return that is negative, so your power is larger in the vertical. Or you can have actively rhymed puppies, as Kyle Thiem told me in his seminar last year, and that does include puppies being thrown by tornadoes and water hitting them and they freeze. I'm just joking, guys. Just joking. So what might this all look like? He did say actively rhymed puppies in his seminar last year. I'm not joking. What might this look like? We have a reflectivity image, and then we have this nice ZDR image on the bottom right. Okay, so we've already talked about reflectivity, heavy rain rates or heavy precipitation rates, large diameters of droplets, larger diameters of droplets, in the center of these convective clusters. And then you can see, co-located, we've got ZDR returns of, I don't have the scale on here, but I can tell you that's about 1 to 2 or so, 1 to 2 dB or decibels. But what about all of this stuff out here in this really low reflectivity return? What is that? Guesses? It's not ground clutter. ZDR is really, really large. That scale ends at about 8 or 9. What might that be? Low reflectivity, really, really high ZDR. No, not wind. Nope. Cloud droplets are almost perfectly spherical. And with a weather service radar, you probably wouldn't see clouds. It's not sensitive enough to see it. Other guesses? Think about what I just said with possible targets for high positive ZDR. Raindrops and insects. Yeah, it's clear air return, as we like to call it, because it's not meteorological, so automatically it's clear air, right? Those are all insects. Birds, possibly, mixed in there. But mostly insects. And if you watch a radar, if you watch the national mosaic of Weather Service radars, if you go on weather.gov and watch that loop as it goes across the country, you can see as nightfall comes, you can see all these insects coming out. Because you see this big expanded area of all these really low reflectivity returns from each radar across the country because the insects are coming out at night. But their ZDR return is really, really large. Because insects, if you think about, say, a raindrop, okay? What, about that big or so? What, bee is what, that big? Wasp? I don't know. It's big. It's really big. And the power coming back, they're elongated. Their bodies are very elongated. So you can actually see that they're flying either this way or this way. Because if you go around to this region and this region, their differential reflectivity returns aren't as high. So the scatter, the power that they return, depends on the orientation relative to the radar beam. So they're all probably flying this way, where their bodies are more elongated relative to the radar beam. Less so down here. Does that make sense? Now, I said earlier, using radar scope, you should always use expert mode. The reason is all of this stuff, all of this reflectivity return goes away if you turn off expert mode. Can you make a valid conclusion about what's there if you turn off expert mode? No, you don't have everything. You are meteorology majors, all of you, I think, or meteorologists. There are some actual meteorologists in here, okay? You are experts. You should be. So know your variables and always use expert mode. So that's my second rant for the day. Now, differential phase and specific differential phase. Getting a bit more complicated. That is the differential propagation of the horizontal and the vertical wave of the radar. Okay. So what that means is if the radar waves in the horizontal and vertical are in phase when they're transmitted by the radar, they might go through a thunderstorm. And is there more water in the vertical or the horizontal in a thunderstorm? I just said it earlier. What are raindrops shaped like? Horizontal. They're horizontally aligned. There is more water in the horizontal than there is in the vertical. So, is the speed of light constant? Roughly, but no. If you're in space, it is constant. Unless you get near a black hole. I assume it speeds up. But in the atmosphere, the speed of light is not constant. And especially when you go through water, it is not constant. Why do we see, if we put our hands in a swimming pool, why does it look like we all of a sudden have a broken arm? It's because the speed of light is not constant there. Okay? So it actually slows down. So if there's more water in the horizontal than there is in the vertical, will the horizontal wave actually slow down more than the vertical wave? Yes or no? Yes, it will. And it does. So you take the phase of these horizontal and vertical waves and you subtract them from each other. And then that is your differential phase. Okay? And that's measured in degrees. And then you can take your specific differential phase by taking the derivative of this and saying that the phase at some range minus the phase at a range that's closer to the radar divided by 2. Why do we divide by 2? Nope. Why would we divide by 2? Radars the beam has to go out and back, right? It's got to go out and back. So we divide by 2 and then multiply by the difference between this gate and that gate. Okay? And so what that tells us is the stronger that derivative, the stronger your KDP signature, the more liquid water that is there. And the important thing to differentiate between ZDR and KDP is that ZDR is weighted towards the larger drop. Why would that be? Think back to the radar equation that I showed you. Why would ZDR be weighted towards the larger drop in the volume? Grad student, why would it be? You do, I guess, to the 6th power. Yes. It's the sum to the 6th power. Okay? So your ZDR is actually weighted towards your larger particles in that volume. KDP is weighted toward about the median drop in that volume. So what might that tell you? The liquid water content of that volume. How much water there really is. The whole reason why we have dual polarimetric radar in this country is not because of tornado detection. It is because of flooding. It was pitched to Congress because we wanted to get better at estimating rainfall in this country. Understand when streams are actually going to flood their banks and flood entire towns. Okay? And so when scientists, when NOAA, whoever, went to Congress and said, we need better radars, we need dual polarimetric upgrades for each radar in this country, it was because of flooding, not because of tornado detection. Am I right, Dr. Clazel? So, to prove to you that you can see higher rain rates with specific differential phase, you have this nice little supercell type structure. It probably wasn't actually a supercell. But then you see these KDP returns that are really large. And again, I don't have a scale down here because in radarscope you have to mouse over to see the numbers. But I can tell you that the differential phase the specific differential phase, or KDP, is really, really high there. And that's because there's so much water in that core of the thunderstorm. So the phase of the different waves are becoming greater. Does that make sense? Okay, and now on to one of my favorite things. Correlation coefficient. Don't worry about the equation. Not worried about it. The important thing to understand about correlation coefficient right now, until you take Dr. Mike Biggerstaff's class in your senior year, is when you have a bunch of different drops in a cloud that the radar is looking at, and they're all about the same shape, same size, their correlation coefficient, rho HV, is approximately 1. But if I have, say, a really large raindrop, a hailstone, and a couple of small drops, that correlation coefficient reduces because there are a lot of different types of particles there. There are a lot of different sizes. There are a lot of different shapes. Okay, so this is really useful to us, especially when we're talking about tornado detection. This is a figure from Jim Kurzo's paper in 2015 in Monthly Weather Review. You have reflectivity here and Doppler velocity here. You can see the nice shear here where the tornado is. And this is actually from PX1000. It's one of the radars I showed earlier in the talk when I was showing all the different mobile Doppler radars around the country. And this was positioned on North Base during the Moore, Oklahoma tornado in 2013. And so you can see as the tornado is entering Moore, you can see in the correlation coefficient field, here's 1 at the top of the scale. And in the rain region here, rain and hail region, it's near 1. Okay? But then when you look down here, there's this nice kind of almost circular lowering in rho HV. That is debris. That is shingles, houses, pieces of houses, actively rhymed puppies. All sorts of different things that are flying around in this tornado. Okay? And this is a really useful thing. Why would it be useful to us as meteorologists? Think about the southeast. Nighttime. Yeah, can't see. Rain wrapped. Absolutely. That's another good one. Is that what you were going to say? Yep. So, geniuses. Time for a quiz. This is the same storm. I've already shown you there's correlation coefficient hole. Where is the tornado? Is there a tornado? Where is it? And just for your reference, this is reflectivity. This is velocity. It's a very noisy velocity field. This is ZDR, and this is rho HV. So I'll let you look for just a second. Is there a correlation coefficient hole, yes or no? Is there a lowering in correlation coefficient? Raise your hand if you say yes. What do you think? You're a scientist. Why? There's no tornado? I can tell you there's a tornado on the ground.
Really?
Yep. Although that's redundant. So there was a tornado. Yeah. I could see his face. There was a tornado. Why is there no correlation coefficient hole?
If any of you ever do that on air when you graduate, I will send you an invoice. Anybody so much as says tornado on the ground, I will send you.
Yep. And he will. He's not joking. I'm going to have an invoice in my mailbox tomorrow. Why is there no correlation coefficient lowering there?
Nothing being lost.
Yeah, it's too soon. The tornado was just started, okay, at this point. This was 1947-44. And the tornado was on the ground at 1946-30-ish. So it had been on the ground about a minute.
Where's the couplet?
The couplet is right there. Yeah. So it is there. But good, you all passed my quiz. This is not a tornado. Good. And this is not a tornado. Okay, so it's inconclusive based on rho HV only. Now, what about this? Yeah, it's pretty obvious. Yeah. There's definitely a lowering, almost a circular lowering in this case. Doesn't necessarily have to be circular. But there is a lowering. That is from debris. And you can see the strong couplet and radial velocity. So good. You all passed the quiz. But what about when you have this? This is the power of Twitter, guys. These were actual tweets sent out to whoever was listening saying that there's a CC hole here in this image and there's a tornado. Do y'all see it? I know where it is. It's right here because there's a little triangle right here. Tornado's here. But what about all those? How is the public supposed to know the difference between this and that one 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 and these and this one and that 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 one? There are literally tornadoes everywhere. I want to go back and charge each of these people dollars.
The vice president for public affairs called me and told me I had to stop calling people stupid on Twitter. Setting an example.
I will do it for you. Guys, if you're using Twitter, if you're going to put this out on social media, be responsible. Use your power wisely, okay? And actually be responsible. Indicate what you mean before you put it out in La La Land for anyone to go and look at it, okay? And that's exactly my advice. Stop posting all these ambiguous photos, okay? I'm not saying any one of you have done it, but we as meteorologists and meteorology students should know better. And we should know when we need to call someone out, maybe not call them stupid, but we should call out the misuse of dual pole variables when it's out there on social media, okay? So, the final thing that I want to get to, and I'm running out of time, final thing I want to get to is what I've been talking about from the beginning, radial velocity, okay? So a radar sees if I have a 5-knot southerly wind, okay, here's the wind vector here, and at each point along this circle here, that's a constant range for the radar. The radar's centered here in the circle, okay? If I were to look at each one of these points, see what the radial velocity return would be at each of those points. When the wind is perpendicular to the beam, it's 0 knots. You will see exactly 0 there, okay? When it's about 45 degrees, you'll see 3.5 knots. Go do the trig to prove to yourself. And then if it's at 90 degrees, you'll see 5. But what happens here? It's -5. That's because it's inbound, okay? The wind is moving toward the radar, okay? So I won't go into all the details of why, but here's what is output on the display, okay? So in this case, again, I like to use the Moore tornado because it kind of hits home. This is an image of the Doppler velocity as the Moore tornado was ongoing. At this point, it was in the middle of Moore. It was very near the Warren Theater at the time. And here you can see inbound where we're representing those with cold colors in this case. So the greens and the purples here. So all the Doppler velocity indicates that the wind is moving this way in the tornado, and then moving that way on the other side. I think everyone should generally know why that is. So it's rotating cyclonically or counterclockwise. And then the warm colors up there represent positive flow or outbound flow, receding flow. Okay? So just remember that. But I said earlier here, we're seeing the tornado. Is that true? You can argue. I'll let you and Dr. Clazel argue if it's $1 or not. I would say it is, because it all depends on the radar's location. This is an emulated image of a hypothetical tornado in a radar simulator, and of a tornado, and it's indicated by this little black circle here in all 3 images. And in this case, the radar was positioned at 3 kilometers away from the tornado. This case, about 10. This case, about 30. So, tell me, folks, can you see the tornado? Maybe. Probably not really, because guess what? A radar is a filter. It's taking an average. It's not taking the maximum. It's not taking the minimum. It's taking an average. So, no, you're not seeing the tornado. This case, you're definitely not seeing the tornado. This case, you're definitely not seeing the tornado. Okay? So, no more saying there's a tornado on radar. That's not right. You do not see the tornado circulation. You see what? Mesocyclone. Yeah, larger scale. Yeah. So, my favorite thing on Earth, the red and green are touching. This is my favorite thing. Where is the tornado in this image? And I will not take silence. Where is the tornado in this image? I have even put X and Y coordinates on here for you. Come on, someone speak up. Where do you think? Ben, where do you think? 2010. About here? Any other guesses? No, I'm telling you, there's the tornado. The red and green are touching. There's tornado. Yeah, this is my reaction when that happens. Just because the red and green are touching does not mean there's a tornado. Here's why. Image I just showed you. The radar is right here at 0, 0. Outbound, inbound. What is that? Convergence. That is the updraft. It is confluence, yes. You are absolutely right. That's actually a Dr. Becerra thing there. Yes, it is convergence or confluence, as we'll rightly say it. That is azimuthally oriented. That is not radially oriented. It drives me up a wall when I turn on the TV during a tornado outbreak and the red and green are touching and there's a tornado there.
Turning on your TV during a tornado outbreak is also $1.
Yes. Where am I supposed to get my information, Dr. Clazel? I understand that. I do it for the entertainment. This is radially oriented shear. Okay? And again, is there a tornado there? What's your answer, yes or no? Maybe. Maybe. You're not seeing the tornado circulation. So maybe there's a tornado there. So to end my portion of the talk, I've gone through a lot of different things. I've gone through reflectivity, differential reflectivity, specific differential phase, correlation coefficient, and radial velocity. Okay. You guys, as meteorology students, as you finish your bachelor's degree or just beginning your bachelor's degree, you guys have the responsibility to understand what these variables mean. And what makes a great meteorologist is to understand the patterns that are associated with certain signatures. As Dr. Jeff Becerra puts it, pattern recognition makes a great meteorologist. And as my father told me once from his mentor in college, and my father is listening right now on the live stream, Dr. Mark Orr, his mentor, said, "You see what you know." That is one of the most true statements that I can think of. Because whenever we as meteorologists look at a synoptic chart, look at a radar image, we see what we know. We are automatically drawn to the most interesting feature that sticks out in our minds. And that is a real danger, guys. We forget to look at all of the different variables, at literally the entire image, take it all in, instead of just going and saying, oh, there's a nice supercell there. Okay? You don't need to do that anymore. You need to understand the entire picture. And that is your responsibility, ultimately. You are a scientist. You should question everything. You should question when someone says there's a tornado on radar. You should question when someone on Twitter says there is a CC hole and there are 1,000 CC holes, okay? You should question that as scientists. And the reason you should is my favorite quote from Dr. Richard Feynman. So you begin by being uncertain as to what the answer is. The question of doubt and uncertainty is what is necessary to begin. For if you already know the answer, there is no need to gather any evidence about it. If you go in assuming that you know the answer or someone else knows the answer, what's the fun in that? There's no fun in that. You should go look for yourself. And that is my rant for the day. And if you use your power wisely, I will be very excited and very proud of all of you. So thanks for listening, guys. So while I take any questions that you guys have specifically for me, you're welcome to get up, take a restroom break, get more food, whatever, and then we'll start with Dr. Klaisel's presentation in just a few minutes.
Everybody good? So I don't need. I can just use that, I guess.
Yeah, it's locked in there, I think.
This, I have to take the mute off, right? Yeah. Duh. Duh. How's everybody doing? Well, first of all, I'd like to apologize. I only know like 2 or 3 of you in the room. I have probably the best job on campus. I have more fun than anybody certainly on campus does. I used to teach in School of Meteorology. I'm also the director of the Oklahoma Climate Survey and the Oklahoma Mesonet down on the 2nd floor. But for the last couple of years, I have been working as university meteorologist in the OU Office of Emergency Preparedness. And so that has been so much fun over there that unfortunately it has taken me out of the teaching realm over here, at least temporarily. And so I apologize that I know very few of you. But what I'd like to do first of all is sort of a mini introduction. Come visit. If you have any inkling to be involved in either emergency preparedness or in decision making or anything like that with meteorological information, by all means come and see me. I'm in 2900 in the Oklahoma Climate Survey Mesonet Suite when you come off that 2nd floor door into the building. So many of you probably come in the 1st floor door, probably can't swipe that 2nd floor outdoor yet, but many of you who can, I'm just that office right off the 2nd floor entrance. As soon as you walk into the climate survey, I will be the office with the unmistakable Longhorn paraphernalia on the wall, so you will know that that's mine. Yes?
Are you the professor we're supposed to go like?
Yes, I'm sure that's the one. I'm sure that would be me, yes. But I am also going to be teaching a course in the spring. So the second thing I wanted to do was a little miniature commercial. Meteorology 4743 is getting its own number, and 4743 is weather forecasting for decision makers. And what we do is each week put you in the hot seat with people who are making decisions using weather information. It will be offered in the spring. It's 4743. It's Tuesday, Thursday morning from 10 to 11:15. So 10 to 11:15 up here in 5930. I taught this course 2 years ago, back to back in 2 different years, and I think the students had a tremendous amount of fun. We've got several students who are in that class who are now working in the emergency management realm post-graduation. So what we do in that class is we actually bring in decision makers. So the folks from the U.S. Olympic Committee, the rowing, the boathouse district up in Oklahoma City, how do they use weather information? How can they certify world records? When you're training people who are going to finish gold, silver, bronze literally in hundredths of a second, how do you take advantage of the atmosphere to give you that edge? Things like that. We will have somebody from OU administration. One semester we had President Boren come in and visit and sort of give you a scenario. What would you do? Would you cancel? You know, instead of tweeting at him, Debo, cancel classes. You get to actually be in the hot seat and see what it's like to make decisions like that, but against other information. In other words, how much money is the university losing to administrative leave? How much money does it cost to clear sidewalks, to clear roads, to put down the ice melt? All of those things have a cost associated with them. So we do a lot of cost-loss modeling against risk in association with what's the better solution. For example, Marilyn Manson concert in Pennsylvania not 4 weeks ago, with a storm bearing down on the concert at an outdoor venue. The individuals running the venue decided that the risk of a riot and injuries and potential fatalities if they canceled it midstream was greater than the risk of somebody being hit by lightning. So they actually made the conscious decision to keep the thing going. Well, what happened? Nobody got hit by lightning, but the venue did, and they lost power. And when they lost power, the concert ended. And what did the people do? They rioted. These are the things that happen, right? So that class, 4743, will put you in the hot seat week after week after week with a different set of people who will come in and take you through the decision-making process, whether that is in an ice situation, an athletic situation here on campus, like may have happened in the last couple of days, and those kinds of things. All right? So what I'd like to do tonight is to give you a little bit of a preview of that course and the things we will do in it, but piggyback off of what Addison just did in trying to get you to get out of this mindset of going from what you see to what you do without any thought in between. All right? And that's usually where the finding of a dollar comes in, is when you bridge the gap from see to do without thinking about it first. And so what I'd like to do is theme this, refuse to misuse. Radar is one of the most preeminent tools used by meteorologists everywhere. How many of you have radar on your phone? Leave your hands up if you are not a professional meteorologist. Why do you have radar on your phone then? Is it possible that we've put a tool for decision making in the hands of people who are not qualified to do it? So what you're saying is that if I took the playbook for the Ohio State Buckeyes and I handed it to you, would you have had the same success? Yeah. How much, Addison mentioned it. You have to practice, you have to practice, you have to practice. And a lot of people who don't practice, it was mentioned, Dr. Furtado mentioned it with respect to the forecast. Right? The only way you're going to get better forecaster, to be a better forecaster, is to forecast. The only way you're going to be better at radar is to use radar. Not just when there's a supercell nearby. Okay? Not just when there's a supercell. So what I'm going to do in the next 30 minutes or so is give you some examples of misuse. All right? And this is going to be highly interactive, and we're not charging $1. We're not taking names. We're not ridiculing anybody. We're just going to lay it out there because I want some honest feedback from you about how you think about some of these things, okay? So I'm going to give you a hypothetical storm. And this hypothetical storm you've probably seen if you are from anywhere in this vicinity 1,000,000 times over. How many times have we seen a supercell thunderstorm southwest of the Oklahoma City metro area? And what breaks loose, right? People are on television, it's wall-to-wall coverage, and so on and so forth. So what I'm going to do is I'm going to give you some givens with this storm, okay? The given is that this batch of reflectivity is headed northeast. How do I know that? Well, because I looked on TV and somebody said, well, that's the way it's going. And made a list, right? A list with times. Newcastle at such and such, Bridge Creek at such and such, the airport at such and such, Spencer at such and such, and there's a list, right? Therefore, it must be so. Yes? I have a question for you. Your own perception of risk, given that this storm is moving this way, would you feel safer if you were currently located in Zone 1, the circle, or Zone 2? How many of you feel safer at this time, storm moving northeast, in Zone 1? How many of you feel safer in Zone 2? Note, no hands went up, right, for Zone 2. So what you collectively just told me is that you feel better in a National Weather Service severe thunderstorm warning than you do in an area that has no warning at this time. Wow. What were you basing your answer off of? Yeah. All right. Cool. That's certainly possible. It's moving away. That's also certainly possible. And how many times have you seen this on your television set or your radar screen? All right. How many different ways of assessing the atmosphere do we have besides radar? A bunch. Good. Good answer. A bunch. All right? You could have said a hell of a lot, a plethora, I don't care, whatever it is. All right? Could have been anything. A bunch. Yet, when you have the opportunity on your phone to make a decision or looking at the television set to make a decision, how many of those are you shown? How many of those other data sets are you shown? Or have we gotten so fixated on radar that radar becomes the primary mechanism by which we communicate, now I'm saying the collective we, meteorologists, particularly in central Oklahoma, communicate risk how? Weather risk. It's with radar. Bless you, is it not? Primarily. Okay. So I will also tell you that every time we poll emergency managers, and I've done this same exercise statewide, that the result is identical to what you just gave me. Every emergency manager says, I feel a hell of a lot better in that warning than I do up there, not in the warning. There's something wrong with that sentiment, especially if you start thinking about other data sets. So I'm going to add a data set and re-ask the question. I'm only going to add one new data set. Cloud-to-ground lightning. And I heard, right? I'm going to ask the question again. Are you at greater risk in Area 1 or in Area 2 at this time? And why did you change your answer? You're telling me that the addition of one single data set completely changes your situational awareness of what's going on around you.
Talking about at this point in time or 20 minutes in the future?
Now. Oh, so you're already saying that I'm going to be at risk here at some point in the time. So you're already path casting this, is what you're telling me, right?
Well, I mean, thinking ahead, yeah.
Right. Okay, good. That's fine. There's nothing wrong with thinking ahead, right? I'm not trying to put you on the spot. Because this is valuable exchange. How we think about these data sets is in fact how many people think about the data sets. And if we can get into the heads of how the people think about the data sets, maybe we're better at communicating risk to people. Okay? Rather than just kind of doing it our way. Right? Because we have our own way of thinking about this. You're already thinking 20 minutes down the road and thinking, I really don't want to be on the southwest side of Moore or at the airport. At this point, though, if I'm a soccer game in Chickasha, I got problems. Right? Because where are all of these CGs occurring relative to the radar imagery we're seeing? They are outside the precip. Over half of the lightning fatalities occur when it's not raining. People who wait for the rain before they take action have put themselves at unneeded risk. If they take action, that's great. You've still minimized your exposure. But you could have done a better job, right? So here's an issue where you have a storm moving off to the northeast, we assume, and a whole bunch of cloud-to-ground lightning going on here where there is no precip falling at the ground. But think. What creates lightning? Why am I seeing so much lightning in an area where there is very little reflectivity? Does that make sense? Hold that thought, okay? Hold that thought. Takeaway 1, before we go on with that thought. Although radar data is a great weather situational awareness tool, the limitation of radar discussed this evening demand that you use these data in concert with other data sets. How many of you actually do that when you look at radar scope on your phone? That is way too few hands, right? You have to be able to process multiple data sets to completely assess your risk. If you are only providing one data point or data set as a meteorologist to your public, you're likely doing them a disservice, okay? And you can make mistakes. Having radar data on an app or a laptop does not magically enhance your ability to assess weather risk. In fact, in many cases, it can lead you to misrepresent or completely miss the actual risk. And we see that time and time again. Let's go back to our hypothetical storm 20 minutes later. Note that the National Weather Service on this hypothetical storm has now issued a new warning. A severe thunderstorm warning that is right along the path cast into the southwest side of the Oklahoma City metro area. This leads to an interesting question. If I'm on the campus and I have one of those newfangled phone apps that beeps me when there's a warning because I was told to download it by a numerical person that's like number 4, number 5, or number 9, just sort of throwing numbers out of a hat, right? If somebody associated with a 4 or a 5 or a 9 told me to download an app because they would let me know if I was in danger, has that gone off? No. But what do you suppose the risk is at OU, given this incredible amount of cloud-to-ground lightning on the southern side of this hypothetical storm? Something's going on there, right? Something should be, but of course if we took lightning data away, what would you be thinking? We got missed, right? We're missed. Yeah, the Norman bubble. Ooh, yeah. The hypothetical Norman bubble. Truthfully, if this white cloud-to-ground mess is not there, what are you already thinking about the risk to our campus? Yeah, we're done, right? So let's say, for example, that there is a hypothetical women's softball game occurring at this time on our campus, and that the NCAA has a not-so-hypothetical 6-mile radius rule for lightning to stop play. I've drawn the 6-mile radius in black from the soccer game, hypothetical. Is there anything going off on anybody's phone app in Norman? Is the game continuing? Absolutely it is. Because the policies you've put in place dictate there's no warning, there's no lightning within 6, you're still playing. Should you still be playing? All right, so here's where the policy and the meteorology are sort of orthogonal to one another, right? And this is what we're going to do in the class next spring. Talk about how to align policies with what we see meteorologically to help alleviate as much risk as we possibly can. Oh, by the way, if you had decision triggers based on the 30-30 rule or any of that kind of stuff, you're still playing, right? And you've heard of the 30-30 rule and with lightning and all of that, yes? No? 30-30 rule. All right. So the 30-30 rule was put into place because what you would do is you would see lightning, listen for thunder. If that was 30 seconds or less, which indicated inside of 6 miles, then you would have to wait 30 minutes before you could restart, and every new lightning bolt within 6 would restart that 30-minute clock. The 30-30 rule. All right? I am telling you now, if I so much as see you counting, I am going to fine a family member at your funeral. Because if lightning is already within 6, you standing there counting is not alleviating your risk. Right? Don't get killed while counting. Good. All right, so let's go forward in time to a hypothetical 3:45. Uh-oh. All right, so what's going on at 3:45? Well, school dismissal is in progress across the city of Norman. That's 15,819 kids being turned out onto the streets. Is it raining? Is there cloud-to-ground lightning? Is there a crap load of cloud-to-ground lightning? Crap load is a highly technical term for get your ass inside. All right? Oh, by the way, hypothetically, the OU classes are going to release at 3:50, right? Because 3 to 3:50 you're, and then suddenly you're out, right? Everybody's running around on campus at this time. There are as many weather threats to life and property outside the pretty colors as inside. Do not allow your eyeballs, when you open your radar app, to go immediately looking for what? Pretty colors, right? You can't do that. What do they show you on television? Pretty colors. In fact, they won't break in and cover live unless what? You got pretty colors, right? Something everybody is drawn to. Your eye is always drawn to the colorful blobs on radar images. You have to resist that temptation. By the way, this is not a hypothetical storm. This is now 4 o'clock. That dark orange red thing is a tornado warning. Because at this time, there is a tornado on the ground in Norman, cruising its way through the heart of Norman, impacting 3 different schools along the way. And oh, by the way, we got people running around on campus like crazy because it's still not raining on campus. How in the world did this storm get from what it looked like here moving there to this? Well, something was going on the south side of that storm the entire way. I asked the question earlier, what would cause that much cloud-to-ground lightning in an area with no reflectivity? On tilt 1. What are you always looking at? How many of you have radar scope on your phone? Pull it out right now. Open radar scope. Tell me how many of you default to BREF 1 or Super Res 1, BVEL 1, SRVEL 1, 1, 1, 1. Holy hell. 1. No. Stop it. Right? Stop it. You'll see why in a minute. Well, this is a perfect example why. I want you to get out of the mindset that when you see a blob and you see a cone, that the blob is going to look the exact same way that it did at the beginning, at the end. This is what it looked like at 3. That's what it looked like at 4. Did anybody mentally visualize this outcome an hour later than this? Not unless you live through it. April 13th, 2012. Yeah. With a lot of stuff going on. I have that event to thank for my current job. Because I was trying to tell them, seriously? You still want to have that soccer game? Well, the rule's 6. Well, I don't care. We'll probably have a tornado before this is all said and done. Shouldn't have said that, but that's what happened. All right? These are the kinds of things that we get in our head about how we move things along that are problematic. A lot can change in 60 minutes. Storms are dynamic. They are evolving. This is takeaway number 3. Misconception by advection. Stop advecting things the way they are. How many of you do that? You animate it, right? First thing you do is you animate it. Yes. Yes. And you're animating tilt 1. Yes. And then you're watching tilt 1 do this over time. By the way, do you know that that's not the same altitude off the ground, each one of those time steps, right? Because the beam, Earth is curved, beam is straight, unless it's being super refracted, subrefracted, and all the other things that can happen to the beam. You're not looking at the same altitude. This is not an amorphous blob. This is not a block that you put in the water and watch it go somewhere. This is a different cut of the storm as the storm is moving. The cut you just saw is now above the beam. It's a new cut that you see in the next image. That cut is downstream again, the next one. It's a different port of the storm. How many of you have said, wow, that storm's really getting strong as it's getting closer? And then, wow, as it goes away, it's not as strong anymore. Has nothing to do with the intensity of the storm. Has everything to do with where you're looking based upon whether the storm is moving toward or away from and at what altitude that beam is. You've got to stop moving things around as blobs, okay? Storms don't stay the same shape, intensity, speed, direction, etc. during their lifetimes. They are also not impacted by interstate corridors, rivers, or the city of Moore, regardless of how many people say so. So we're going to try another one, because you guys were a miserable failure in that one. God, and so many people killed, it's not funny. So this is now Winston-Salem, North Carolina. I love Winston-Salem, North Carolina. Anybody in here aware of DCI, Drum Corps International? All right, so I have been forecasting weather for DCI for the last year, and this year got an opportunity to was like the highlight of my weather career. I got to be sort of the personal meteorologist for Phantom Regiment all season. So it was really, really cool to get to sort of follow them around and provide them with lightning information and so on and so forth. And they were in Winston-Salem, North Carolina on this night, with a set of storms cozy moving along at about 19 knots. 19 for hours. Been watching multi-cell lightning storms move to the east, due east at 19. That was the cone that comes out from the SCIT algorithm on the radar. And at the current speed, they'll reach Winston-Salem, where a DCI event is going on at 10:20. The event is due to end at 10. How are we doing? Can we get the whole event in? Event's supposed to stop at 10. Storms have been well behaved, moving at 19 the entire evening. And oh, by the way, this is composite reflectivity. This is the actual base reflectivity. Notice that it doesn't look that much different than composite reflectivity. Where the heck is the closest radar to Winston-Salem, North Carolina? It's in Roanoke, Virginia. Up on the roof, right? So we're already talking about a beam that's where? Pretty high up. And a beam width that's very big, and so the resolution's not going to be so good. So, asked the question at 8:58 Eastern Daylight Time. We've been watching these things well behaved, move at 19, slated to arrive at 10:20, and about 9 o'clock they're saying, Kevin, are we going to be able to get this in? Kind of see some flashes way out there on the horizon. Is that lightning? We going to get it in? What do you tell them? What do you tell them? I'm asking you, what do you tell them? It's a real question. It's not hypothetical. Not a hypothetical question. What do you tell them? You tell them no? What do you mean you tell them no? Okay, everybody wanted to see Blue Devils. They're last. Right? Everybody wants to see Carolina Crown and Blue Devils. They're the last two. All these people paid all that money. And I'm saying, well, what time are the storms going to get here? That's the next question I'm asking. What time are the storms going to get there?
People are leaving.
What?
People are leaving your event.
Are they?
If it's ending at 10, you said.
It's 9 now. We still got an hour to go. 5 cores to perform. What am I telling them? You guys are going to be in this position. Seniors, where are you?
I would say shut it down.
Why?
Well, one, you said you can see lightning, and so that's already become a threat.
Okay. I'm just seeing flashes. I mean, like, in the far... I'm seeing heat lightning. It's North Carolina. I'm seeing heat lightning in the distance. Probably in Missouri somewhere.
But yeah,
Do I have any reason to call this event off if I'm only using this radar data? To be honest, is there anything here? The only reason you're worried is because I'm presenting this case, right? You're already suspect. All right. Thank you for being honest. This is 3 minutes later, 9:01. What just pops up halfway between the storms that are set to arrive at 10:20 and halfway to the venue? What happens? Oh my God, that's 3 minutes later. They just asked you at 8:58, and you said what?
I said shut it down.
You did. You absolutely did. You absolutely did. But has your risk timing been altered in 3 minutes? Since the 8:58 to the 9:01, has that 10:20 changed? All right, good. Yes, it has. So 10 miles out, and we use a lightning threshold of 8. 10 miles out at 9:01, you have a new cell. Is there any way that you could have anticipated that? I see heads nodding yes. How? Knowing your upstream environment is fantastic. At this point, I've been watching these storms for 3 hours, and not a single storm has popped up in front of this line or this multi-cell cluster. Not a one until now. So let's go back to 8:58. So here we are at 8:58, and this is the location of the new cell. Anything there? Don't you have tools at your disposal? Other than that stupid tilt 1 that you're looking at the whole time? Where do reflectivity cores originate in convection? Aloft, not at the ground. The last place you want to look for risk in a convective environment is where? The ground. How many of you default into tilt 1? All of you. Take out your phones right now. Whichever radar you default to, change the tilt to tilt 4. Tilt 4 first. It's top down in a convective environment. The early reflectivity is going to be aloft, not down low. The last place it gets is low, which means if you're using tilt 1 primarily, if you're not looking at upper tilts, you've just done yourself a disservice. These are other data sets. Even though they're within the radar family, still other data sets that you can be using. You've got to be looking at tilt 4 first. Why? Because there it is at 858. If you're looking at tilt 1 and providing information based upon tilt 1, you just screwed up. Because at 858, that sucker was already there. And oh, by the way, if you go backwards, it was there a full 14 minutes before it ever showed up at tilt 1. You start getting new returns out ahead of the line. It goes from nothing to something. And you got 14 minutes lead time before it even got to tilt 1. Because you looked at tilt 4 first. And by the time you get to 921, lightning is within 8 miles of the venue. By the time... What time did we clear the venue? 10 after 9. 10 after 9. Cleared the venue. Use all of your data, not just a data point, and not just the one that you're comfortable with, right? Which is tilt 1. And I don't know why that happened. How you can get a whole bunch of meteorologists to unanimously default into tilt 1. How does that happen? How many of you, actually, be honest, actually look at the upper tilts when you query radar? That's not enough hands, right? That's not enough hands. A convective storm is what? It's vertical. It's vertical. You're using a horizontal technique and you're going to use one cut and that is going to solve your problem, right? How do you know that the cake is chocolate or vanilla or strawberry if it's iced? How do you know? You got to eat it, right? You got to dig in. That's what you're dealing with radar. The icing at tilt 1, you don't know what's in the cake unless you eat it, right? Unless you go all the way through it and eat it. Takeaway 4, you are provided multiple tilts for a reason. Use them. Lightning storms are vertically developed. In most cases, precipitation-sized particle and hail develop aloft. Therefore, upper tilts can provide earlier clues to risk than the most popular Bref 1 scan. Oh, by the way, TV stations use unanimously lower tilt. Always lower tilt. Don't. That's all I will say. All right, case 3. Last case. Indianapolis, 8:35 p.m., August 13th, 2011. Many of you know this event, okay? And if you know this event, that's fine. Tell me what's going on the radar image. Thank you. You resisted the urge to do what? Say squall line. Many of you said gust front, outflow boundary. Now, I did provide an assist. There are 6 arrows right here, all pointing at it. All right, so I've helped. Our venue for the evening is going to be the location of the X. It's called the Indiana State Fairgrounds. This is the warning product at the same time as that image. All right, from the National Weather Service, it's a severe thunderstorm warning, and it includes all this stuff. Note, all of these places are west of Indianapolis, west of the metro, west of downtown. The venue is east. So if you were focusing on the squall line, it was approximately 20 miles out, and it was moving east, rather behaviorally pretty well, at about 25. If that's at 8:39 and the warning has destinations through 9:05, all the warning destinations ended right about here through 9:05. So what time does this weather threat make it to the Indiana State Fairgrounds? After 9:05. Thank you. Good. And if you time it out linearly, which I said not to do, remember misconception by advection, if you do it advectively, then you come up with something on the order of 9:15 as an arrival time to the venue. But you guys pointed out something. You guys said, whoa, but there's an outflow boundary. There's a gust front. Okay, cool. Let's focus on the gust front. This is 8:44. Here's the gust front. We are going to pretend as if this doesn't even exist, right? Because I just told you, don't get fixated on the blobs and the pretty colors. It is approximately 4 to 5 miles out to the west, and it's still moving at that sort of slower speed. And so the 8:44 radar, if you do the linear interpolation, you get an arrival time of what? Okay, 8:53. 8:53. Right, 9 minutes. You can do the calculation. So what time did you get the 8:44 radar image on your computer, your app, your phone, your whatever? Yeah, it's probably 8:47 or 8:48 or 8:49. And even if you do this exercise in your head, what time does this line, this thin line, which represents, for those of you who don't know, there are a ton of freshmen in here and I'm not going to assume things. Outflow boundaries created like when you turn a hose onto a pavement driveway, hits the ground, spreads out. So the cold air rushes out of the storm, hits the ground, spreads out in front, provides gusty winds, all kinds of things. Okay? And so that is what's creating this zone of convergence where the particles get kicked up at that interface and wind up at the venue at 8:53, right? So here we are. By 8:44, by advection, the estimated time of arrival of the thin line is 8:53. By advection, the estimated time of arrival of the squall line, the pretty colors, is 9:15. So let's go to the venue. See what's going on there.
As you can see to the west, there are some clouds. We are all hoping for the best, and the weather is going to bypass us, but there's a very good chance that it won't. So just a quick heads up before the show starts. If there is a point during the show where we have to stop the show on stage, what we'd like to have you do is calmly move towards the exits and then head across the street to either the Champions Pavilion, the Blue Ribbon Pavilion, or the Pepsi Coliseum. And then, once the storm passes and everything's safe, we're going to try our best to come back and resume the show, which we have every belief that that's going to happen. Get ready, because in just a couple of minutes, we're going to try and get Sugar Land on stage. Have a great show.
What did you learn from that? Did they have a plan? Well, sure they did. They had a fantastic plan. Right? First of all, the first part of the plan I completely disagree with. The very first thing he said, we are hoping for the best. Hope is not a plan. All right? Get that out of your plan. We don't hope. But after hope, we had what? We think the weather, but it might get here, blah, blah, blah. And then here's your instructions. We're going to go to this hardened facility right behind this pavilion. We're going to go to this place right behind. They had a plan in place, and honestly, those buildings are sitting right behind this grandstand. They didn't have far to go, and it wouldn't take them long to get there. All right? What time was this video, do you think? 8:44. Yes, it was. It was the same time as that radar image that I just showed you. So at 8:44, we have somebody come out on stage and says, you know what? We know there's weather. We hope it misses. If it doesn't, we're going to do the following. All right? I'm all in favor of let's do the following. I'm not so in favor of we hope it misses. I think you always have to assume you're going to get hit. And there were several visual cues during that, one of which, this one, even prompted pointing from a variety of crowd members in front. Did you see that? When you saw that lightning strike, everybody was like, woo! Did you see that? Yeah, that must be the stuff that's about to miss, right? That we're hoping. So they must know, right? They think it's going to miss, so I'm not going to be worried about it as long as he's telling me we were hoping for the best here. 17 seconds in, 42 seconds in, and 58 seconds between 8:44 and 8:45, you're seeing multiple lightning strikes from west through north of the venue. Would you like to see the radar at 8:53? Wow, you guys did great. Timed that thing on the money, right? 8:53. What's going on at the venue at this time at 8:53 with the thin line right on top of it? It's getting very windy and it's very bad at 8:53, correct? By the time, what time did you get the 8:53 radar image? Is that a problem? You're already behind, aren't you? Oh, by the way, at the same time, or very shortly thereafter, a new warning comes out from the National Weather Service in Indianapolis. Severe thunderstorm warning remains in effect, blah, 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 and it will be near where? The Indiana State Fairgrounds at 9:20, which is still another half hour from now. So this is the very real part of what you are embarking upon. Your career, your ability to protect life and property is to prevent this. You're not going to prevent that stage from coming down. There were reasons it was going to come down. But did there have to be people in the first 4 rows? If you had made the decision when you were seeing the lightning, if you had made that decision, would there have been anybody in even the ground seats? They would have all gone which way? Away from the stage toward the building, right? That was behind the grandstands. 7 fatalities, over $50 million so far in lawsuits. And this is from the post-action report. State Police Special Ops Commander Brad Weaver was watching an ugly storm moving in on radar via his smartphone. What do you suppose ugly storm is code for? Pretty colors, maybe? What do you suppose they fixated on? The squall line. The storm was expected at 9:15, but arrived 30 minutes earlier. Did the storm arrive 30 minutes earlier? No, not the storm as defined here. The storm as defined here blasted through here at 9:15 while recovery operations were underway, putting that many more people at risk, which could have all been avoided up front with a proper implementation and a proper determination of weather, not just monitoring pretty colors. So your radar thin line arrived at 8:53. You probably received the image on your app or your phone at 8:57. The storm was expected at 9:15 to 9:20. But you know what, folks? That stage did not come down at 8:53. It came down 2 minutes after the announcement at 8:46. Why does the stage come down at 8:46 and the thin line not arrive at your site on your radar app until 8:53? Exactly. Thank you. Say it out loud. Thank you. Radar never, ever identifies a threat at the ground. Ever. The threat is at beam height, and beam height is not at the ground. And you have to know by now that things are tilted. So if you've got a radar that's going through a thin line and into a squall line, that radar beam is now off the ground. And there may not be a 1-to-1 correspondence between the reflectivity in the gust front at beam height and the actual position of the gust front, which is likely out ahead of that thin line. You cannot follow thin lines around thinking that that's the risk. That's not what you're timing. You have to put your meteorological thinking caps on and understand that what's going on at the ground is likely well in front of the thin line that you're watching. I think it's an absolute disservice that we put maps on our imagery. I really do. Because all it does is lead to confusion, because there is a natural inclination to take what you see on radar and do what with it? It happens on television all the time. We do it too. Well, the tornado was at the intersection of blah and blah. You know, the gust front just blew through Guthrie, but I can tell you that 5 minutes ago on the mesonet, it was gusting to 56. Okay? These are not occurring at the ground. You have to put yourself in three-dimensional space and understand that you're never looking at risk on the ground. So I'd like to kind of give you sort of 6 closing thoughts here. The availability of weather information, particularly radar imagery and warnings, is at an all-time high. You can get 360,000 hits on free radar imagery for smartphone, 8 million hits for weather apps on the iPhone, and there are 1,000 weather-related apps between Apple Store and Google Play. 1,000. And they all have downloads, so people have these things. That's how they're making decisions unless you come in and help them. Okay? Most of them provide radar imagery and warnings, and that's it. How many of you see actually real-time cloud-to-cloud and cloud-to-ground lightning on your app? A few of you do. Okay? If you're supporting an event, you better. And if you're supporting an event, you better start with Tilt 4. Especially in convective season. If I see any of you look at Tilt 1 first, I'm fining you $1. How many of the websites actually come with instructions on how to appropriately utilize the data and the weather information? So we get back to my original question. Are you all professional meteorologists? A few of you are. Yes, I understand. But you're all using a very difficult to use, even for the experts, tool at your disposal in many cases to make life and death decisions. How many developers of websites even offer training on how to utilize them? That's why we're here this evening, you know, to kind of give you a heads up that don't just kind of use it out of the box and think that you know what you're doing. There's still so much. It's like Addison mentioned earlier, you've got to question everything. You have to question everything. Life-threatening weather feature identification detection is difficult even for the pros, yet we give lay users the playbook. If we're going to give you the playbook, we've got to do a better job of coaching you up. Goes back to the Ohio State comment earlier. You know, if we're just going to walk around with somebody's playbook, it doesn't necessarily mean we're going to have success on the field. Same is true here. Just because you have data at your disposal doesn't mean you're a great meteorologist, right? You've got to learn with it, practice with it. Same thing that Addison said earlier. The weather information we provide, show on TV, lends itself to misconception by advection. Don't be a victim and always assume that you are already 10 minutes behind. If you're making decisions and you're using radar, you're already behind. The latency of the data plus the tilt, you know, the beam factor, you're not looking at the ground, and most everything is slanted in such a way that on the ground it's out ahead of what you're actually seeing on radar. You're behind. You're probably already 10 minutes behind. And if you're only using Tilt 1, you're probably hosed, as we would have been in both of these cases. If Tilt 1 was your only way of making decisions, you probably got the venue in trouble, you got the campus in trouble in the first case, and you killed 7 people in the third case. Misuse of meteorological information resulted directly in 7 fatalities. That can't happen. Folks, that cannot happen. You have to be careful how you use it. You have to be diligent. You have to query more than one piece of information, more than one tilt. That's the way you become a professional meteorologist. Being weather ready is not, let's see how close I can cut it. It's also not hoping. And with that, I am done. And thank you for hanging in there. I know it's after 8 o'clock, so I appreciate it.
I'd like to thank both of our presenters tonight for an absolutely stunningly fantastic presentation. This was beyond my wildest dreams. Thank you guys so much for doing this. Really, really appreciate it. So let's give them another round of applause. So before we start closing things up, does anybody have any questions for our presenters from either presentation? Anything at all?
What's the class number?
4743. Tuesday, Thursday, 10 to 11:15 in the spring. Yes. Since it's a 4,000 level class, it'll be junior, senior. If there are sophomores that want to come in, it will be by instructor permission. I think I had to list the intro courses. I think they made me list the intro courses, the sophomore level intro, because it was listed as a 4,000 level, and you can't list a 4,000 unless you have sophomore prerequisites on it. So, but if somebody is really passionate about taking it, just come see me and we'll figure out what we can do.
Awesome. Thank you guys so much for coming. This was our first workshop of the year. We're going to have another one next month and one last one in November. We've also got other events that we'll have, such as OWL Game Night, which is going to be in November as well. So definitely pay attention. If you guys didn't know, we have our Facebook page, Oklahoma Weather Lab. Definitely follow us there because we have announcements about events such as this one on there, and event pages for events like this. And otherwise, I want to thank you all for a really great evening, for coming here, for listening to this stuff. And I hope you guys really internalize all this information and apply it in your social media use, in talking to friends, and trying to teach people about the weather. So thank you so much, and I'll let you all go now.
Yeah, this is a huge turnout, so thanks for coming and thanks for hanging with us.